Okay, hi everyone and welcome back. Time is now 10:40 there on the East Coast. Before we begin this second session of today, let me just give a quick shout out to everyone who's joining from Japan, China, Australia, New Zealand. For you guys, it's the middle of the night, so kudos for you for hanging in there in true astronomer fashion. The first speaker we have today is an invited talk by Tiziana Di Matteo, who is faculty at Carnegie Mellon University. And she is going to tell us about the epoch of the first quasars in cosmological simulations. So take it away, Tiziana.
Hi, everybody. Thanks, Darren, and everybody else for inviting me to tell you a little bit about cosmological simulations here. And thanks, everybody, for the great talks we've heard during the conference. Melanie couldn't set the stage any better. And we are here, we are talking about black holes as critical players of our cosmic history, and how we try to understand these black holes with cosmological simulations is basically the subject of my talk. It's one of our greatest theoretical and observational challenge of modern astronomy. And this sort of image sort of very briefly illustrates how they participate in every stage of our cosmic history, much as we've talked about over the course of this conference. As I said, I'm here to tell you a little bit more about what can we attempt to learn from cosmological aerodynamical simulations. This is indeed what Melanie has told us. They're sort of the state-of-the-art simulations that do constitute these days our primary avenue for understanding structure formation, from the very large scales all the way to subgalactic scales, all the way to giving us some understanding of how black hole growth can be embedded in this. So this certainly should be one of our primary place to go to when we want to capture some of the understanding of black holes in connection to galaxy formation. So I'm going to be focusing mostly on what these kind of tools can teach us about the high redshift universe, so the first quasars and first galaxies, as indeed Madeline has reviewed in detail lots of other stuff. So the central problem here, again, something that we've talked about quite a lot, is understanding how we end up with these giant supermassive black holes at very high redshift from some kind of seeding mechanisms that often are simulations of this large volume universe simulations that don't capture directly. But again, we heard descriptions of what this could be. Okay, so these are only tools that are major tools at high redshift currently for which we have observations. So our main tool to start understanding this theoretical challenge and this observational constraints that we have from the black hole population at high redshift. So what am I adding here is that indeed we know that these objects are extremely rare. So in order for us to actually capture them in simulations, we need to meet this challenge of going to extremely large volume simulations. So I'm adding just a little bit more about this kind of tools. So the development of extremely large volume simulation, large volumes that are sufficient for us to actually capture more than just one or two of these objects, but a statistical sample consistent, of course, to what observations have been telling us that quasars are roughly found at redshift 6 and above. They're rare, they're roughly 1 per gigaparsec volume, very roughly speaking. So the challenge has been that we need to do this enormous simulation at this gigaparsec volume, yet preserve the kind of resolution that we have in simulations that we heard about earlier on today, because obviously these quasars form in these very small galaxies, things are very small. So we are capturing this enormous volume of the early universe, right, that we are able to probe and find rare quasars in, yet we want to maintain the resolutions to tell us to as much as possible about the origin, the physics, and that pertains to this problem itself. Okay, so this is an example here of one of the simulations which we are trying to meet this challenge of doing this very, very large volume. So this is a gigaparsec simulation, and the resolution very consistent to sort of state of the art, and therefore also the physical realism of the state of the art that we heard again this morning about. So what is the compromise here is that what has to happen, something has to give. So when we go to this extremely large volume, they're typically run to only relatively high redshift. So the simulation was run only down to redshift 6, for example. Okay, so the models are fully consistent with all the other models that we heard about that for simulation that are run to redshift 0. So what do we have then? We have simulations now that really directly probe the environment of high redshift quasars. And so I want to just give you some highlights, let you take a peek with me through what we are seeing in the simulations, right? So some highlights, some sort of results. There's a lot that can be said, but I'm just going to pick on a few things so that you can get a peek. So this is the fundamental sort of thing that I want to emphasize. Okay, so in this plot, there is the black hole mass. Every single blue point in this plot is a black hole system, and the halo mass in which it finds itself in. So what is sort of, I want to highlight now that we have this very large volume, of course, we have finally large samples, or relatively large samples of 10 to the 12 solar mass halos. Those are putative halos that are a host of these high redshift quasars, as we know from observational constraints, from theoretical arguments, and so on. So finally, here we have them. We have these huge volume simulations. We have a bunch of them. And this is what we're seeing. So sort of 1 and 2 are going to be sort of things that I focus on a little bit. But the fundamental thing is that for a given halo mass of 10 to the 12, which is at this redshift at 5 sigma peak in the density field, we have a variety of black holes, right? So there are certainly these 10 to the 12 solar mass halo are indeed the ones where we find the 10 to the 9 solar mass black holes, but they could also be the ones where we find much smaller masses black hole that would not be considered the first quasar. So there's a large variety of history. So so picking a 10 to the 12 solar mass halos doesn't give you automatically 10 to the 9 first quasar black hole-like object at redshift 6 and similar. So now that we have this sizable fraction of halos, they're still very rare. So even in large volumes, there's just a set number. But what do we see? Why is that so? What drives this result? So not every 10 to the 12 mass halo is going to have a first quasar. And so why do some get it and why some don't? So just to let you have a peek, this is, for example, the density field centered at around a 10 to the 9 solar mass black hole, a first quasar. As such, right, in the simulations, right? So prototypical object 1, an example, okay? So this high density peak is the 5 sigma peak, is the halo 10 to the 12 solar mass. And this density field around the quasar that is in the middle is color coded by temperature. So there's a black hole sitting, this is megaparsec scales around this region. The red kind of colors represents sort of the temperature in this region. So there's actually a black hole that is accreting and is applying feedback to the surrounding regions, and that's what we see. But I want to move quickly to contrasting this to the region 2, which is another 5 sigma peak, another 10 to the 12 solar mass halos at the same redshift, where we don't actually grow the black holes very efficiently. So immediately, just going from this to this, it's very apparent there's something in the density field that is different about these two objects, right? So this is much more concentrated, this very peaky spherical overdensity, and this is much more spread out and elongated. Okay, so I want to kind of zoom in. This is still region 2, where we do not have a very large black hole growth or very early growth in this high sigma peak. And I want to sort of slice this in one dimension just to sort of highlight what's going on. Okay, so this is this region so if we draw it in one dimension, we actually trace it, right? So this is a sigma peak in the initial condition, a 5 sigma peak that is shown on the left-hand side, right? So it's still a 5 sigma peak. And when we evolve this 5 sigma peak from the initial conditions, this large density region that is present in our initial conditions naturally as given to us, it ends up, if we look at with, you know, a very large of a density that is sort of represents this sort of more spread out, more elongated regions that has many different peaks. The region which has the massive black hole, the first quasar, starts off in the initial conditions. Again, the same height is a 5 sigma peak, which eventually collapses in the 10 to the 12 solar mass black holes. But just simply, and that's a direct prediction from, you know, our Gaussian initial conditions, not all peaks will be created equal, or not all 5 sigma peaks are the same. They have different shapes, like different shape, curvature, and so on, right? Although they have the same height, okay? They have the same rarity. And that's what happens, you know, this peak, by being a lot more concentrated from the very initial conditions, will undergo gravitational instability and grow. And this is, it will be just a lot peakier, a lot more centrally, which is sort of represented in the 2 dimensions by this region. And this is just a natural prediction, and our ability to be able to sort of sample through the different sigma peaks in these very large volumes where they do form the 10 to the 12 solar mass halos, and which one then, as we go back to what we've, you know, our simulations, which ones are actually naturally giving us the strongest inflows into the galaxies, and therefore the fastest, quickest growth for the central black holes. They tend to be these objects, these extremely sharply peaked, very isolated regions in the, which are tend to be in very isolated regions, which means in regions of relatively low tidal fields. Okay, this is sort of to go directly at the accretion, right? So these are the same kind of regions, 1 and 2. So how do these large scales relate directly to the central black hole? Here is going back from the redshift 6 black hole, tracing every single particle in these brown colors that has actually gone into the accretion rate onto the very central black hole, which we do model directly in the simulations. The tracks are just some sample, a subsample of these particles, right? So we plot on top every single particle that has made it all the way into the central black hole in both cases. And again, we see that accretion occurs onto the black hole, accretion occurs from these large scales all the way from every direction, sort of quasi-radially in this very concentrated peak. In the ones that in these regions that are much more spread out, these much broader peaks of the 5 sigma peak, accretion has a harder time to occur, right? These are the particles that actually make it into the black hole. They can only make it sort of transversely perpendicular to the main overdensity where they have lower angular momentum. This is all at very high redshift, okay? So the fastest growth is typically achieved in these regions where we have this quasi-radial sort of very low angular momentum, almost quasi-spherical collapse kind of peak. So that turns out to be very important, right? So from the first plot, why are the black holes not growing everywhere? Because we need some extra conditions, not just the height of the peak, but these sort of regions which grow in isolations and allow for this extremely fast growth for the central black hole. Okay, turning this into more directly, what does the overdensity of galaxy look like then? It's natural that a lot of the systems would, and now I'm showing that directly the galaxies around these regions, around the supermassive black holes, most often will look like relatively isolated environments, right? With not great overdensities of galaxies. This is what is shown in on the right-hand side, right? So this is the central galaxies, and the cross shows them these big black holes. There are other objects around, but the scenarios on the left-hand side is again another massive black holes in the center at the same redshift. It's way rarer. So there is a variety. Of course, not peaks are the same, just much like I've been saying. There's a variety of histories, but we see more often than not that the environment of quasars in terms of overdensity of galaxies, because it naturally picks a very high redshift, I emphasize very high redshift in particular, this relatively isolated kind of places, it will be found itself in a relatively low density regions in terms of the overdensity of galaxies around the quasar, over first quasar, high redshift quasar. Okay, so this is one point. I want to now talk to also a new simulations that we're carrying out, trying to push a little bit into lower redshifts, but still with very large volume. So same sort of philosophy, we're trying to push to the possibly largest volume and still have as much resolution as possibly can. This is this ASTRIT simulation, and I'll talk about in general in this and other simulations some of the highlights of some improvements, some steps that we are taking toward a more realistic representation of black holes in this type of simulation. I'm not going to go too much onto all the physics. Again, we talked a little bit about these full physics simulations that include the subgrid model for galaxy formation and black holes. I'm going to concentrate a little bit more on some of the new aspects that we've been able to implement in the simulation. So typically the cosmological simulations, as you heard, they have a fixed seed mass. What we're able to do now at higher resolution a little bit is to implement a power law model for seeds. So we actually seeding black holes across masses between 10 to the 4 to 10 to the 6 within the same simulations, no longer just one single seed. Another improvement that has happened in a recent series of simulation, not just this one, some others as well, is that we are able to have a bit more realism in the black hole mergers. So black hole mergers often in this cosmological simulations occur by sort of pushing the black holes together by repositioning them on the potential minimum. And sort of there's some kind of forcing in this, and which can give us different effects, both repercussions on the actual growth history of black hole and certainly on the merger rates. So now we're able to sort of follow them all the way into the in spiral and not operate anymore, but with this repositioning. So just to give you an example of what does it actually mean, we have seeded black holes at lower seed masses than, say, this is just one example, in another similar volume, the IllustrisTNG, something that is recent and you heard about earlier today. So in yellow here, it shows just this new dynamic range that in this large volume simulation, we're able to probe now, and sort of up here is indeed the trace of this black hole, sorry, this power law seeding that we've been able to do. So extend a little bit from, seeding extremely massive objects, right, in our cosmological simulations to going towards 10 to the 4, 10 to the 5 sort of seed black holes and spread across some kind of distribution. Then this is the significant sort of figure, in an illustration, sort of what happens to black holes when you reposition them on the left, right? This is often what we were doing. So the black holes are coming closer to each other. They actually belong to a different subera, different galaxies. So there's a galaxy merger, they come in closer and then eventually merge. Now we are looking at a situation that is much more like on the right-hand side, where dynamical frictions are bringing in spiraling these two black holes together in a much more realistic fashion and much more physical fashion. So these are sort of two highlights of what's been happening in the most recent numerical large cosmological simulations. Okay, there are small steps. This is not amazing physics, but they just make a difference. So if we go to each single system in these large volumes, what do we have? We have, I zoom into two particular systems. We have galaxies, of course, and millions of galaxies in the simulations. Here, zooming into two examples. We have galaxy mergers that occur. Down here, just example, we have a light curve, right? An evolution of the black hole mass that grows by accretion, and it's regulated by feedback, and its own sort of light curve. At the bottom here, we're showing at every instant in time as this in these two particular systems we're zooming in. Their accretion rate turned into a luminosity of, say, these two black holes that are actually eventually merging in these two examples in these two cases. But we have these in large statistical samples, so we're also able to sort of validate our simulations by looking at the overall populations of galaxies, right? So we have objects for which we follow the physics all the way into the inner regions of galaxies, but this very large sample. So again, you've seen luminosity functions and all these different statistical means that we're able to go and say, are our black holes, we make improvements, we have a model for a subgrid models for galaxy and black holes, how do they fare against current best observational constraints? So this is an example of the luminosity functions of galaxies, right? So we want to get black holes, but we need to get the galaxy population right as well. at redshift all the way to redshift 3 in this case. So in blue is simulation prediction and the data points, the constraints from observations. We could do it also for directly the luminosity functions of AGN at high redshift. We have various constraints. These are particularly in the X-rays, again, with data points and gray regions for the data and the lines for the simulations. And again, we've heard a lot about sort of statistical constraints and how the simulations fare against them. So this is just sort of consistent with what we heard today. And again, a lot of discussion, with this large population of black holes, we can go after, comparing to the black hole galaxy relationship, the mass of the black hole, stellar mass, and so on. So I want to just say that in connection to the things that I said that we're doing now a little bit better, right? We're following the black holes all the way into the central regions. What are we seeing? We're certainly seeing that gas accretion is the dominant channel at high redshift for the growth of black holes. So this is the mass fraction gained by black holes in different bins of black hole mass. And up here is basically close to 1, the mass that is gained by accretion as opposed to mergers. So black holes definitely grow by accretion in our simulations predominantly, although accretion and mergers and the seed mass plays an important role, right, particularly in the lowest mass black holes and mergers in the higher mass ones. I want to talk a little bit more now that we have maybe just a bit of a broader range in terms of seed masses. They're still pretty chunky. They're still between 10 to the 4, 10 to the 5, and so on. So they're not the absolute smallest masses, but what we can look at, sorry, at the bottom here, that doesn't appear, it's actually the seed mass. Sorry, there's an issue here, but okay. So this is the black hole mass that we measure at redshift 6 for the full population of black holes in gray. And down here, there should be the black hole seed mass at which the black hole was seeded up to redshift 10 or 15, okay? So this is basically a range that was going from 10 to the 4 to 10 to the 8. And basically, we're not seeing any trace that by even redshift, sorry, in this case, it's redshift 3, but even at redshift 6, this distribution is extremely flat. So black holes that we observe, the first quasar at redshift 9 and 10, sorry, at masses of 10 to the 9, 10 to the 8, 10 to the 9, and so on, they don't keep their information about the seed masses. They've definitely erased it. This is consistent with the fact that they've grown by accretion, consistent with the fact that they've mostly grown at high redshift in predominantly at Eddington phases. They've grown exponentially, right? So but we're able to trace this a little better. When we look at this population of black holes, we have lost the information on the seed mechanism on their seed mass. Laura also talked about black hole mergers and various jewels. Here now we have full populations, right? And this is just for fun, just a sample of them, of black holes that merge and emerge, and maybe just a little more realistically, not by stitching them together, but evolve and eventually merge in galaxies at high redshift. This is perhaps the place where we have the best bet of a high redshift of getting some sense of what the seed mass is, but it's still very challenging. So these are prediction of merger rates for LISA, because these will occur in the frequency that are relevant for space gravitational wave interferometry such as LISA. And this is the number of mergers as a function of redshift, about redshift 3. That is split up in various samples, but the bottom line is that above these redshifts, we are not going to see many mergers. These mergers occur typically with a delay compared to the galaxy mergers because of the dynamical processes that are bringing the black holes in, that we're able to follow a little better, although there are still other steps that are not resolved, but they will take a while. So we really just expect one black hole merger at this high redshift. This is sort of highlighted by redshift 3. So, and these will typically, this is the mass distribution of the mergers. Most of the mergers at this high redshift will typically occur. This is the F with black holes that are still at the seed mass. So this few putative merger events that we are expecting or hoping to see at high redshift are likely to be those that are resulting from populations that are close to the seed mass, close to 10 to the 5 or so for both N1 and N2. So I just want to make one last point that, of course, there are some objects that have higher masses, and they would also have mergers. The rates of these mergers are just very, very low. These events are just too infrequent to expect for us to be seen. And so, you know, the mergers in the population of black holes of 10 to the 7 all the way 10 to the 9 are going to be the only ones that will have an electromagnetic counterpart that is observable, but they will not be LISA events just because of the rarity of these events, right? Although the dynamical timescales for the mergers is shorter, they're simply too rare. They are not going to be frequent. So something else that we're able to move into as we look at these large volume simulations with a little bit of increased realism, to just go and see how well electromagnetic signals and gravitational wave signals from this early population of black holes can teach us about their emergence and their growth histories and the process of the black hole seed, the origin of the black hole seeds. So
5 minutes.
Yeah, I'm actually done. So I'm going to stop at that, and thank you, and take question.
Well, great. Thanks, Tiziana. And stunning visuals. I always say that the theoretical universe is much more beautiful than the observational universe. Simulators can make these astounding movies and visuals. But,
yeah, I agree.
Unfortunately,
fun to play with.
Unfortunately, it's not the real thing, though. That's the problem. But anyway, that's a minor detail to us. Do we have any questions? Please raise your hand or put your question in the Q&A. While we're waiting for that, maybe I'll ask a question. I think this merger prescription is really, really interesting, and you showed lots of results from that. But I noticed on an early slide, what I'm wondering about is the timescales that you need to resolve in order to get these black hole mergers to happen. And I was watching the time in the left and the right on an early slide where you first introduced it, and one was tens of millions of years and the other was hundreds of millions of years. So could you just comment on the time resolution you need in the simulations and how accurate you can be there?
Yes, absolutely. Yes. So this is by no means the end of the story. You're right. So basically what we are able to do is to follow a little step closer to so we're still in these cosmological simulations. We only follow the process down to the resolution limit, which still remains 100 parsecs, right? So in terms of timescales, could be other processes that could delay the mergers further at all the scales that are not resolved. So there's the other dynamical processes that become relevant there. There's further dynamical friction below the resolution limit. And then there's loss cone scattering processes like that can further delay the mergers. So as Laura told us about, and we've done some of that modeling, that can be sort of done, and Luke Kelly and other people and herself, a group, have done this sort of as post-processing. So I think what I've shown you today, and we've done some of that post-processing as well, in terms of trying to understand how much more delayed would this object be if we accounted for other processes that should be relevant at below the resolution limit. So I think the overall result is that right now, at least at the level of what we understand, is that the kind of delays that we're seeing by improving a little bit our modeling of the black holes down to kilopart is close to at least half of what we would expect. So the order of a few hundred million years is close to half of the overall delay that we would expect from these other processes when we model them sort of semi-analytically as post-processing. So we're getting a little closer, but there's still some uncertainty. Bottom line, I think the rate that I tell you about, or roughly 1 merger per year, maybe becomes a half of, but I wouldn't be much more pessimistic than that, I think, from what we are able to see right now.
Okay, thanks. We have a question in the Slack by Marie Lau. Marie, if I unmute you, do you want to ask your question directly to Tiziana?
Hello, am I unmuted? Yes.
You are.
Yeah, so I think in some of the slides, I think it's early. You show that one improvement in the asteroid simulation is that you try to reposition the black hole to the local potential minimum. But how do you know that the black hole cannot be slightly above the disk or slightly displaced? I think I've seen that in other simulations, and I don't think it can be really ruled out observationally. So what's the purpose for doing that?
Okay, yeah, so sorry, maybe I wasn't very clear at that point. I was just saying that often that's what was done, but we no longer do that. So we do not reposition, and that's done in asteroid and other simulations. So that was just sort of a kind of a shortcut that we kind of had to take because of the limited resolution that some of the previous generation simulations had. So what was done is that the black hole sort of because there was too much wobbling around, there wasn't enough dynamical friction that we could capture so that the in-spiral of the black hole all the way to the central regions of its host galaxy would be captured well. I think in asteroid and other simulations, now the resolution has become competitive, realistic enough that we can actually follow the in-spiral, that inflow of the black holes into the central regions without applying any repositioning, which would be much more, it was just a compromise between, you know, the kind of resolution we could achieve, but it's not ideal.
And do you always find that the black hole will sink to the center now that you can really simulate a dynamical friction?
Very good question. We find that it will sink to the center if in some time scales, and that time scale can be very long. So effectively, no. So we are able to make better predictions, which I didn't show today in detail, but better prediction for the populations of black hole, the occupation numbers, the population of black holes within a galaxy, as you know, different population black holes at different masses, as they come into galaxies, they will take you know, different time to sink in. So the heavy ones typically sink in faster, the lighter one don't sink as fast, and because they're not repositioned automatically, we're able to sort of capture that a little better.
Thank you.
Okay, great. Thanks, Marie. We have a question in Q&A from Giovanni. Giovanni, let me just bring you up. If you want to ask your question, I'll unmute you.
Yes, okay. Can you hear me?
Yep, go for it.
Okay, I would ask if there are, which are the best astrophysical objects in terms of quasar, protocluster, clusters that can be crucial in relating the results of this kind of simulation and the results from the observations?
Oh, very tough question. I agree very much. I think Melanie said this morning, there's no real silver bullet. Unfortunately, we need everything. So as it was emphasized, you know, the faint end of the luminosity functions, AGN, is a good constraint on, gives us some good handle at the early growth and the seeding processes particularly. The studies of the environments of early quasars, the first quasars, also give us a constraints. To me, what we're finding is exactly what is expected from the simulations. There's a variety of environments, a variety of overdensity around these objects, and it's natural that we find that given our predictions. And then in terms of obviously opening up this to LISA and gravitational wave signals, I think that will give us another handle on the seed population. So there's everything is game, everything that people are doing. I think Madeline will talk about the host galaxy of the first quasars. I think going after the host galaxy and the property of the host galaxies, I didn't talk much about that because she will talk about that a lot, is also another very fundamental constraint, as we expect the host galaxies in different scenarios for the origin of the first quasars to be a very good constraint. for understanding the growth and the mechanisms at which we get these very large black holes in the kind of scenarios that I highlighted today.
Okay, thank you.
Thanks, Giovanni. Do we have any last questions? You could raise your hand if you want before Tiziana leaves us. No? Okay, well, thank you again, Tiziana. That was great. If you do have any other questions for Tiziana or any of the speakers in this session, please jump over to the Slack, and I'm sure they'll be more than happy to answer you there. Our next speaker is a contributed talk, and that is Analis Evans. Analis is a graduate student from the University of Florida, and she'll be speaking on building semi-analytic black hole seed models to analyze seeding conditions using IllustrisTNG. Thanks, Elise. Take it away.
Hi, thank you for having me. My name's Analis Evans, and I'm going to be talking about building semi-analytic black hole seed models to analyze seeding conditions using IllustrisTNG that I'm working on with my advisor, Laura Blecka, and our postdoc, Aklant Bomick. And one of the bigger questions that we're interested in here is, how did those supermassive black holes observed at roughly 6 through 7 grow so large so quickly? And as Melanie talked about earlier, there's all these different seeding mechanisms that work together with mergers to create different black holes of different masses. But semi-analytic models are a useful tool in trying to understand constraints of black hole seeding better and figure out how and when black holes are seeded. And so the tool we're using is IllustrisTNG. IllustrisTNG is a cosmological simulation suite. It includes Planck 2015 collaboration constants measured from cosmic microwave background. It includes gravitational physics as well as magnetohydrodynamics, and it has a built-in Arapo code, a moving mesh grid that moves with all those equations. TNG models galaxy formation and evolution, reproducing black hole scaling relations as well as other relations. And it also includes several subgrid models, including ones related to black holes. One includes the Friends of Friends Halo Finder. And there's also a black hole seeding model where once a halo reaches a mass threshold of 10 to the 10th solar masses per H, TNG seeds a black hole of size 10 to the 5th solar masses. And they calculate black hole growth via Bondi accretion, and they include 2 modes of black hole feedback, kinetic or thermal modes. And it also includes several black hole seeding criteria values that are ready to be altered for our models. And we're using specifically TNG50, which is the highest resolution, smallest volume box that's able to capture some smaller scale structure and phenomena that the other boxes aren't. So we're taking a hybrid approach to semi-analytically modeling black hole seeding, where we're using IllustrisTNG to identify seeding sites there and populate them with black holes by tracing them through TNG's galaxy merger trees. And we're able to seed black holes in halos with a variety of seeding criteria. And the criteria aren't related to the ones already used in TNG. We also, our models remain agnostic to any one specific seeding scenario. And a disadvantage is that our models do not include black hole growth or feedback that we do have to calculate to include. And but advantages are that it's computationally inexpensive and flexible compared to running full hydrodynamical simulations. So we identify black hole seeding sites and trace them through the merger trees. And we make a few model assumptions. The first being a maximum of 1 black hole per host. So as you can see on the diagram in the right, that allows us to not include to only count one black hole when a merger event happens, like in this blue star case on snapshot 3, we do the count up to z=0. And some other assumptions we make are a minimum gas and total mass criteria, as well as a low average host metallicity criteria for 0.1 solar metallicity or 0.01 solar metallicity. And these halo gas mass metallicity histograms in the red dotted lines show the thresholds above or below which we are going to vary our parameters for our models. So first we do a sanity check where we use the TNG seeding criterion to test our halo model, and we see good agreement between the number of black holes in our model and those in TNG. So it works like a regular seeding prescription. And so now I'm going to show some preliminary high resolution results for our fiducial model, where we vary the host mass in these plots. And so we first can notice that TNG black hole number densities come out differently than the empirical data points that we see in the colored points. And so overall, it's because the black hole mass function redshift evolution isn't there's uncertainty in it right now, and but we see in our 0.1 solar metallicity models that they do span the parameter space of the empirical data pretty well, and we're going to see that it spans regions above and below. And we also notice for the 0.01 solar metallicity models that in this group of data, they do not produce black holes early enough. And then in the top group of data, we're varying the gas mass. And in the bottom, we're looking at high total to gas mass ratios. So here we can see better in the 0.1 solar metallicity models that some of the combinations of cuts span above the parameter space spanned by the empirical data and some below. So there's several combinations that can create reasonable black hole number densities. And this is our only agreeing 0.01 solar metallicity model on the left panel, top left. And but overall, it shows that we in the future we want to lower stochastic seeding so we can consider more low metallicity models, and we also want to look at the larger parameter space for better understanding. So to conclude, we built these flexible hybrid semi-analytic seed models using galaxy properties from TNG, and we traced the sites through the galaxy merger tree. Our models produce a wide range of black hole number densities, including some models that agree with observations and simulations. The models suggest that more physics is needed to paint the whole picture of black hole seeding, and there's still a lot of uncertainty in observations and theory about the redshift evolution of the black hole mass function. And for future directions, we want to explore a larger parameter space of seeding criteria to inform black hole formation models and future simulations. And that's all. Thank you.
Great. Thank you, Analis. Absolutely perfectly timed. We have one question in the Q&A, and that's from Ryan. Ryan, let me just unmute you and you can ask your question. Go for it.
Hi there. Thanks, Annalise, for an excellent talk. My question is, clearly you have this wide range of black hole number densities depending on these different parameters that you put in there. And clearly one really important one is the metallicity. And so I'm wondering, are there observations that we can use to constrain that one parameter. So then we can start to think about things like the gas mass or the galaxy mass.
Let me think about that. Well, in our models, one thing we're not accounting for specifically is Lehman-Werner radiation. And with lowering stochastic seeding and doing more with that, I think we could definitely observe some more low metallicity effects on the model. But first, we definitely have to get more of the low metallicity models to start producing black holes early enough.
Great. Excellent. Thanks.
Do we have any other questions or anyone who wants to raise their hand? I have a quick question. Is your method generally transportable to other semi-analytic models, or is it quite customized for Illustris and the codes you have?
I'm sure it could be replicated in other simulations, but definitely it is flexible in that you can calculate the growth and the feedback and consider different criteria really easily.
Okay, great. Thank you for that. Very nice talk. All right, so we should move on to our next talk. Another contributed talk from Fabio Di Mascia. I hope I pronounced your surname correctly, Fabio. Sorry if not. From Pisa, Fabio is a graduate student, and he's going to talk to us about AGN imprints on the infrared emission of galaxies at the epoch of reionization. Take it away, Fabio.
Thank you very much. So hi everybody, I'm Fabio Di Mascia. I'm finishing my PhD at Scuola Normale Superiore in Pisa. And in this talk, I would like to share with you my results regarding AGN imprints on the infrared emission of Redshift 6 galaxies during the EOR. So first of all, why we can be interested in the infrared emissions in AGN host. So we have a tremendous progress in the recent years about the number of quasars discovered. Now we are almost at 300 quasars at redshift around 6. But there is a small caveat, or a big caveat. They are all UV selected. And if you have a look at the UV luminosity function of the quasar at redshift 6, according to the recent estimate, you have an idea of how many quasars we know so far from the UV. However, if we consider the AGN luminosity function, extrapolating from redshift, the X-ray AGN luminosity function, extrapolated from redshift 3 to 4 up to redshift 6, we see that there is a huge discrepancy of almost of 2 orders of magnitude in for at least the faintest one. So this might suggest that we are missing the bulk of the AGN populations. So, and if so, maybe it will be interesting to look in the infrared if it is possible to find infrared signatures to identify faint or obscured AGN. And second, the second main point that I would like to talk during this presentation is what is the impact that AGN can have on the host galaxy properties. I will focus in particular on the dust temperature. So in order to address these questions, we consider zoom-in cosmological simulations that are focused on the Hanover density corresponding to a 10 to 12 solar mass halo, which is simulated from redshift 100 down to redshift 6. We adopted the suite by Bahrain collaborators of 2028. In these simulations, there are standard prescription for the stellar physics and an additional prescription for black hole seeding growth. And then we were interested in the in particular, we consider two runs of these simulations. A run without AGN, that is essentially a control run in which black holes are not seeded, and a run in which instead the black holes are seeded. That will be a fiducial run that we will compare with no AGN run during the rest of the talk. And then we performed radiative transfer calculation through dust in order to simulate the UV and far-infrared emission from the dust continuum. In particular, we assumed a uniform dust-to-matter ratio and dust properties of the small Magellanic Cloud. And we also included AGN component emission with a power law and setting in particular the volumetric luminosity proportional to the accretion rate of the black holes in order to be consistent with the hydrodynamical simulations. So one of our main results is the following. If we look at the same snapshot, so at the same redshift, the simulations with AGN and the simulations without AGN, and we consider the spectral energy distributions, we see that the simulations without AGN has a infrared to mid-infrared ratio of the flux that is of the order of 100-1000. Instead, if we consider the run with AGN, this ratio drops to 1. Therefore, we find that AGN boosts the mid-infrared flux. And this is very interesting because we can observe galaxies in the far infrared with ALMA, and JWST will already be able to find something in the near infrared, and the proposed origin mission also will look in the mid infrared. So this mid infrared and far infrared ratio can be a signature of AGN activity, and it will be possible thanks to this ratio to unveil faint and dust obscured AGN. But where does this mid-infrared boost come from, first of all? This comes from the dust temperature. If we have a look at the dust temperature distribution of the run without AGN, here I'm showing in the right-hand panel the PDF of the dust temperature. In the blue, you can see the mass-weighted dust temperature that probes the bulk of the dust mass. And in red, you can see the luminosity-weighted dust temperature that is most sensitive to the bright regions. And you see that the dust is relatively cold within 30-60 Kelvin without AGN radiation. But when we include AGN radiation, we find still that the bulk of the dust population, of dust component is cold. However, there is also a warm component that is dust in the ISM closer to the AGN that reaches value above 100 Kelvin. And this dust component is constitutes only a small fraction of the total dust mass, but it provides 50% of total infrared luminosity. So the main takeaway message from this calculation is that the AGN can effectively hit the dust in the host galaxy. And now a natural following up question would be, but when we measure only the far infrared of these objects and we of the quasar host, and we try to infer the star formation rate, can we actually say that that this infrared emission comes only from dust emitted by stars? And in order to investigate this, I will show you these preliminary results. We consider many of the black holes in the AGN run a different snapshot, and we try to compare the star formation rate inferred from the SDE, so as if it were a mock observation, and with the true star formation rate that we know from the simulations. And first of all, we compare these two star formation rates without including AGN radiation. So we consider the same actual simulations, but we do not include AGN radiation in the radiative transfer calculation. And we see that, yeah, thank you. And we see that the two results are more or less consistent when we don't have AGN radiation. But when we actually turn on the AGN, we see that there is a discrepancy between the estimated star formation rate from the SCD. And this is quite evident for the most luminous AGN already above 10 to the 13 solar luminosity. And this discrepancy can be up to almost 2 orders of magnitude. So from our calculations, we find that the star formation rate estimated in AGN host can be actually overestimated by up to 2 orders of magnitude. So I will briefly summarize my talk. We performed relative transfer calculations through dust of Redshift 6 QUASARS galaxy, and we find that the far-infrared to mid-infrared ratio can be a proxy of AGN activity and can be used by current and future facilities to unveil faint and or dust-obscured AGN. And finally, that the star formation rate that we can infer from far-infrared observations can be overestimated by up to 2 orders of magnitude because the AGN can actually contribute to the dust thing. So I'll leave you with my summary slides, and I'll be happy to take your questions. And also feel free to reach me on Slack.
Thank you very much for that, Fabio, and sticking so precisely to time. Do we have any questions? Please post them in the Q&A or raise your hand so I can see that you're asking. While we're waiting for that, I did have a question, Fabian. Can your work provide a sort of a correction to how observations are currently done to provide, maybe give a more accurate estimate of the star formation rate, taking this effect into account?
Yeah, that's a very good question. It's something that we actually are working on. Can be very useful to have such a correction. Yeah, it's a good suggestion. We are working on that.
Some kind of empirical relation, something.
Yeah, exactly.
So Giovanni has his hand raised. Go ahead and ask your question, Giovanni.
Yes, thanks. Did you compare the star formation rate obtained from the far infrared with the star formation rate obtained with the radio band in order to check if there is also this overestimation also in the radio fluxes?
We actually don't have the radio flux from this for these simulations, so we cannot do that. Okay.
It would be interesting maybe to check this thing.
Yeah, it can be cool. Yeah, to check this also for many wavelength bands. Yeah, that's right.
Okay, great. Roman Maya has a question. Go ahead and ask your question, Roman.
Yes, thank you very much. Very nice talk. On top of the far-infrared continuum, have you looked at the impact on the far-infrared emission lines, atomic and molecular lines?
No, thank you for the suggestion. From this relative transfer calculation, we only simulated the dust continuum. But yeah, that could be also interesting to look for infrared lines. Because from observation, that like something that we find more frequently. So yeah, it could be cool.
Yes, thank you.
A quick question from Ryan Hickox. Ryan, go ahead and ask.
Yeah, and thanks for a nice talk. Just to follow up, I guess, on these last two questions, are there any other observations that would be useful for estimating the AGN luminosity, both for getting that and also correcting the star formation, like, for example, X-rays, or if you could go deep enough, some kind of spectroscopic observations?
Yeah, X-ray can be very, very helpful. Also to probably to probe to confirm AGN that we find in the UV or from the mid-infrared far-infrared ratio. But I don't have a prediction for that right now.
All right, great. If you have any more questions for Fabio, please go ask them over in the Slack. I'm sure he'd be happy to answer you there. Our next contributor talk is from Chris Richardson, who is a faculty member at Elon University. Chris is going to tell us about emission line diagnostics with JWST and SDSS, to detect simultaneous intermediate black holes and stellar excitation in redshift 0 dwarf galaxies. I feel like I've just given you a talk, Chris. Go ahead.
Okay, can you see my screen?
Yep, looks good.
Okay. All right, so okay, so hello everyone. I appreciate the opportunity to present today. I'm going to talk about developing emission line diagnostics for active black holes and dwarfs. I'd like to give a shout out to my collaborators that are given below here in bold, who are also in attendance, and I'll be referencing their work as well, so feel free to contact them on Slack directly. So I'm thankful for the great review talk today and the discussion on Monday about the importance of constraining black hole seeds for a galaxy and black hole coevolution. So JWST is going to aim to observe early universe galaxies and constrain this initial black hole mass distribution. But an exhaustive survey is likely going to be cost prohibitive. So local dwarfs can serve as suitable proxies since their physical conditions mimic those in the high Z galaxies. And we can use dwarf AGN in particular to set the lower limit for the occupation fraction in these dwarfs, as well as filling in the low end of the black hole scaling relationships. But identifying dwarf AGN is difficult using traditional methods, and that just comes down to the very nature of dwarfs. So dwarfs are metal poor and star forming, and you can see from the Rhines that all sampled that radio confirmed AGN, dwarf AGN lie in the star forming wing of the BPT diagram. And then if you follow up on those galaxies, you realize they have complex morphology. So they have disc-like structures, spheroidal structure and peculiar ones, and they can also wander around a kiloparsec off center. And so then finally, the hardness of the intermediate mass black hole SED is uncertain. So here we have 3 different models that have fixed black hole mass. And so they give very different accretion disk temperatures and X-ray fluxes. And that uncertainty can then lead to, as you decrease the black hole mass, to having possibly unobserved emission lines like O3. So our goal then is, and it's the natural thing to do, is to incorporate these uncertainties into a cloudy model that's designed to trace this AGN activity in dwarfs. And so a lot of the key features are given here, but I want to draw you to the ones that are in red. So these excitation mechanisms, mixing methodologies, and the open and closed geometries. So these are what separate our models from some of the other ones that are out there. And so I've said previously that the morphology and geometry of dwarf AGN is pretty variable. So the limiting cases that you see here are the ways that we incorporate them into the cloudy modeling. And so the bottom cases are where you have the spectra that are combined after the radiation field goes through the clouds. And this has been used, for example, in mixing observations of pure AGN and pure star-forming galaxies. And so then if we use these bottom 2 cases as sort of like limiting as a case study, we can then ask ourselves, does the theory say that we need to worry about geometry? And we can answer it by looking at what we call these sensitivity diagrams. So we can trace the line ratio as a function of AGN fraction. And so for the 5007 over H beta ratio, as AGN fraction increases, the uncertainty in the line ratio grows to about 1 dex as a difference due to geometry. And so then we can see that this gets exacerbated even further if we add on different SED models and mixing methodologies. So these are here shown in different colors. So each color shows a different mixing methodology or AGN SED model. So there's a lot of degeneracy in this line ratio that we would have to disentangle. So if we think of one more interesting case is examining AGN activity for black holes that are around 10 to the 3, since these are particularly elusive. So on the right, I have the same sensitivity diagrams, but now as a function of galaxy mass. So it's increasing as you move downwards. And there's several interesting trends to note, but one thing that I want to point out is that we find that O3 over H beta remains bright in conditions that are physically characteristic to dwarfs. And that's in contrast to Conadol, which is finding them to be unobservable. And so that means that there's hope that SDSS has already observed this activity. O3 over H beta doesn't trace the AGN fraction all that well. So we do need a different, and there's a lot of degeneracy, so we need a different emission line to really to help us out with that task. And so this is where the O1 over H alpha line ratio comes in. So O1 over H alpha traces the AGN fraction rather well. It's much less sensitive to geometry and the mixing methodologies I showed previously. And so we can think, we can do a limiting case study again and say, well, if we take the limit for high levels of AGN fraction, we realize that the values converge upon those of liners. And so, but you would have BPT diagram indicating their star formation. And so perhaps this is where these 10 to the 3 solar mass black holes are hiding. And there's been some early evidence from Gramadol just posted to the archive that could be the case. And this O1 over H alpha result holds for not only 10 to the 3 solar masses, but also for black hole masses at 10 to the 5. So we use that result to apply it to a dwarf dominated survey known as Resolve. And so Resolve is given down below. You can follow the URL or reach out to Sheila Kahneman, who's the PI, and on Slack. And so her thesis student, Mugdha Palomera, found that applying these models by classifying AGN according to the O1 over H alpha ratio can increase the local dwarf AGN fraction from around 1% up to 15%, which is a pretty large increase and really exciting.
2 minutes.
So now JWST is going to allow us to probe even lower fractions of AGN or AGN fractions than we can in the optical. And so high ionization corona lines have been suggested for finding these AGN. But one of the things with corona lines is that if you see them, then you know that there's definitely an AGN, but not all AGN actually have corona lines. So they're not likely to be reliable enough for a statistically complete analysis. But there's several other emission lines that lie within the Miri band, like neon 3 over neon 2 ratio, that have been good indicators of AGN activity for low mass dwarfs. And they've been used in diagnostic diagrams very similar to the BPT diagram, but in the IR. So we followed up on that by using this diagnostic. And so here's one of those diagrams that you would see from Weaver 2010. And this is a core dump basically of all of our models, where the hatch shapes represent different models for a given AGN fraction, all the way down to 4% AGN. So very little AGN excitation. And the typical demarcation is denoted by x equals 0 on this diagram. And so if you were to go with the Weaver et al. Classification, you would be missing out on a large percentage of dwarf AGN. And so we've redefined these demarcations according to our models that allow us to capture those dwarf AGN. There's still a little bit, even though there is clear separation between the pure star forming and the pure AGN models, there's a lot of degeneracy in the AGN models. So for the fractional AGN activity, a lot of the hatch shapes are falling on top of one another. But there are better emission line diagnostics that we can use, especially with JWST. And 2 of those are the argon 4 and argon 2 lines at 26 and 7 microns. So those line ratios, they are less sensitive to geometry. They show a larger variation for AGN fraction that the other mid-IR line ratios do. And they're valid across a bunch of galaxy mass regimes as well. So these new diagrams that we're showing here, they're based on these lines, based off of those emission lines, and the models show greater separation for lower levels of AGN fraction. And so we hope as the new results come in from JWST that these diagrams are going to be very useful in the same way that the BBT diagrams have been for the optical. So, so the summary is that we have this new modeling suite geared for many of these different physical uncertainties. There's hope that we've observed 10 to the 3 solar mass black holes in SDSS. We just have to know where to look for them. There's a lot of great emission lines through JWST to constrain this activity. And our future work is going to use Bayesian analysis and multi-sector modeling for even more complex topologies. So I think I'm out of time, so I'll leave it there. And thanks.
Great, thanks, Chris. Very important stuff. Do we have any questions? I see one question there from Brandon. So Brandon, please go ahead and ask your question.
Yeah, can you hear me?
Yeah, go for it.
Yeah, so great talk. I did miss the first couple minutes, so I'm sorry if this has been answered in any way. But I was curious as to how much confidence there is in the field of BPT diagrams, how confident we are that liners are in fact AGN, because all the research I've looked into, it's not super well defined if liners are AGN or not. So I was just curious as to your opinion.
Yeah, I think that you could say
1 minute answer. Sorry, 1 minute answer. Yeah.
I could say there's you could say a fair amount of them are AGN, but I really think the liners are probably a mixed bag. So you can use pure star formation and shocks to explain liner excitation as well as AGN, and so I think you really have to take that as a case-by-case basis. I think most people would say that liners are some flavor of it, and there's some other excitation going on other than star formation, but it can't always completely explain it.
All right, thank you.
Yeah, that's a great question, Brandon. We could have a whole conference on that, I think. All right, well, thanks again, Chris. We've come up to the last talk of this session now, and finishing us off is Madeline Marshall from NRC Herzberg. She's a postdoctoral researcher there, and her talk is going to be on detecting high redshift quasar hosts with James Webb. Take it away,
Exactly.
Madeline.
Thanks, Darren. Yeah, so today I'm going to hopefully make you feel optimistic about us detecting the host galaxies of high redshift quasars with JWST. So I'm going to talk a bit about our predictions with the blue tide simulation, and also what our actual plans are with cycle 1 for James Webb. So we really would like to understand quasars and their host galaxies, and in particular study their stellar masses, star formation rates, kinematics, and so on. And one of the key ways that we can do this is by studying the UV optical, both the stellar continuum and emission lines. Now, while this is now relatively easy at low redshifts, unfortunately, this is impossible at high redshift. And so one of the biggest problems here is resolution. So in terms of taking rest frame UV photometry, our best instrument for this at the moment is Hubble. And so here are some images of 2 quasars at low redshift and a quasar at redshift 6. So at low redshift, you can easily see that extended host galaxy structure, and you can make really detailed observations of that. But by the time you get to the highest redshifts, your emission is completely dominated by the quasar. So this shape here is the point spread function, or PSF, of the instrument, which just tells you how the instrument responds to seeing a single point of light on the sky, so an unresolved object like a quasar or a star. And so the reason for this, that it looks like this, is the host galaxies is tiny. So as you go to the highest redshifts, the galaxies are just really small. And so the light is just indistinguishable from the point source. So you can actually kind of get around this by doing very detailed PSF modeling. And this works well at intermediate redshifts, but by the time you get to redshift 6, it just doesn't work. So here's a subtraction of this quasar here, and this is just residual noise. And so with our best instrument that we've got so far, Hubble, we cannot distinguish the host galaxies from the quasars in the rest frame UV or optical, just due to this resolution problem. So that's big problem 1. The second problem is if we're looking for the rest frame optical lines, unfortunately, they're shifted into the infrared, which we can't currently detect. And so the key to both of these problems is, first, we want a high resolution instrument. Secondly, we want something that can give us infrared spectra. And that's exactly what James Webb is about to do. And so today I'm going to talk mostly about problem 1 and our detailed predictions using blue tides to understand whether we can overcome this with Webb. And also I'll be talking about the James Webb Cycle 1 projects that I'm involved with that will aim to look at both of these problems. So Tiziana discussed blue tides earlier today, so I don't want to go into any of the specific details, but basically we use quasars from the blue tide simulation. So at redshift 7, there are 22 of them that are SDSS-like, you know, quite bright quasars that are analogous to those that we will actually be observing. And what we do is we make mock images of each of these quasars using software called SynthObs. And so we make mock images with JWST in a lot of different configurations, and also HST for a comparison. And what we then do is run these images through our observational PSF subtraction pipeline, just as we've done for our real HST images, and we will be for our JWST images. So overall, it's a pretty accurate test of what we should be seeing when we observe quasars and their hosts with Webb. So here's an example here. So this is one quasar and host imaged with both HST and JWST. So HST at the top and JWST here. So if we pass this through our subtraction pipeline, we get no detection here, but we actually do successfully detect the host statistically. And then on the right, we have the host image that we're actually searching for. And so I think the key thing here is to understand that we're trying to find something that looks like this underneath this. And so this, I really think, amplifies just the enormous task that we're trying to undertake by doing this PSF subtraction. But regardless, it looks like it will at least be successful for Webb. But what we can actually do is look at the detailed different observational strategies to see what the best strategy will be. So here we have the fraction of successful detections as a function of wavelength, and I'll slowly step you through this. So first of all, we've got the near-cam wideband filters in 10 kilosecond exposures. And you can see that we're actually detecting 85% or more of quasar host galaxies. So this is absolutely fantastic. We're really going to start to be able to see a lot of these objects. And so here are some images so you can see the kinds of things we'll get when we do the subtraction. We can look at different exposure times, so 1, 2.5, 5, and 10 kiloseconds, again with the images. And we can see that we really need 5 kiloseconds or more to detect the majority of host galaxies. Finally, we looked at MIRI, and unfortunately the success rates are quite low. They're still way better than Hubble, and also will be very valuable for the particularly dusty host galaxies. So we've done this very detailed analysis, and there's a whole paper with lots of results for you to look at if you're interested. But basically, the next obvious step is to actually go and do these observations. And so based on these predictions, we designed a JWST Cycle 1 program, which we were lucky to get awarded 16 hours to observe these two quasars here with near-cam imaging based, as I said, on those predictions in terms of which filters and exposure times to use. And so we're hopeful that after we do this PSF subtraction, we'll be able to actually detect these hosts in the rest frame UV and optical for the first time, detect their stellar masses so we can measure the stellar mass black hole mass ratio. And these objects have ALMA data, so we'll be able to compare the stellar properties to the gas properties and study their environment. So you can actually see these objects have a lot of objects in their field of view. So this is our photometric program, but I'm also involved with some other programs as well. So particularly Roger Windhorst's guaranteed time program. We're observing 2 high redshift quasars with a near spec IFU. So these 2 here. And so one of the key things about these 2 quasars is when we did the PSF subtraction here, it actually revealed these very close potential companions. We haven't determined their redshift yet. And so doing this IFU observations, we hope to be able to understand whether these are actually mergers in progress. Now, finally, and maybe most excitingly, is the near spec GTO program that I'm involved with. And with this, we're looking at 6 high redshift quasars, and we're getting both high resolution spectra to look at the optical emission lines, and also low resolution IFU spectra to try and actually measure that quasar host continuum. And this will be able to allow us to study both the hosts and ISM, CGM, and so on. So overall, I think very optimistic that we'll be able to actually detect quasar hosts at high redshift for the first time. So with our detailed blue tides predictions, it's really certainly looking possible with photometry. And so that's what guided our Cycle 1 observations for our GEO program. And then there's also, a lot of promising avenues with spectroscopy, which will be very exciting. And so as well as those 3 programs that I'm heavily involved with, there's a whole host of very exciting quasar hosts and just quasar generally studies that will be done in Cycle 1. So stay tuned for the next year or so of very exciting results to be starting to come through. Thanks.
Great, thanks, Maddie, for that. We have a question in the in the Q&A. Let me just unmute you, Madeline, and please go ahead and ask your question.
Hi, Madeline, really nice talk. Could you go back to the slide where you showed the success rate as a function of wavelength? Just one thing. So if you see here, so if you just focus on the purple line, you can see that as we go to like larger wavelengths, the success rate increases. And then when you go to a different instrument, which is basically going to even larger wavelengths, the success rate sharply drops. I was wondering why does that trend change?
So the resolution of MIRI is much worse. And then also you've got a lot more noise at those wavelengths as well. Also, this filter here, it gets the Lyman alpha flux from the quasar. And so the quasar is very bright. And so doing the subtraction seems harder. So that's why this one's particularly low. And then, the others, it's more resolution and noise effects that start to, become a problem.
Okay, thank you.
Thanks.
Great. Michael Strauss has a question as well. Go ahead, Michael.
Great talk. Thank you. Can you say something about how useful it is to get observations in more than one band to try to get learn something about the stellar populations, perhaps in the host galaxies or otherwise? Did your simulations explore that as well?
So we haven't, but it definitely will be necessary to get a few so we can actually start to fit some SEDs and estimate what the stellar masses are. I think you could potentially get a rough guess with 2 bands, but the more the better. And so with our program, I believe we're doing 6 filters, so all of these 6 filters.
Okay.
So we should have a really good estimate of, if the subtraction works, of course, of what the SED will be. And
we'll be holding our breath for the results. That'll be very exciting.
Yeah.
Wonderful.
Thanks.
Okay, let's leave it there. Let's close out the session, and I'll thank all the speakers again, not just for their wonderful science, but for sticking so precisely to time. I believe it's midday Eastern there, and unless there are any announcements, I think we're ready for a 20-minute break before the final session.